welcome to this problem walkthrough. Today, we'll explore problem number 1194, detect cycles in a 2D grid. This is an exciting challenge where we'll learn to identify cycles in a grid using efficient techniques. Let's dive in and uncover the approach step by step. Here, we are tasked with detecting cycles in a 2D grid. The grid is represented as an MXN matrix, where each cell contains a lowercase English letter. A cycle is defined as a path within the grid that begins and ends at the same cell, with the path length being at least 4. From any given cell, we can move in one of the 4 cardinal directions up, down, left, or right as long as the value in the destination cell matches the value in the current one. The goal is to determine whether any such cycle exists in the grid. The input consists of the grid itself, with dimensions ranging from 1 to 500 for both rows and columns, and the output is a Boolean value, true if a cycle is found, and false otherwise. For example, consider the first input grid. Here, the grid contains multiple cells with the value A, and we can observe a cycle formed by the following path, starting at cell 0, 0, moving to 0, 1, then to 1, 1, followed by 1, 0, and finally back to 0, 0. This path forms a loop, and its length is greater than or equal to 4, which satisfies the problem's definition of a cycle. Therefore, the output for this example is true. In contrast, for the second example, the grid does not contain any cycles. While there are cells with the same value, no path exists that forms a loop with a length of at least 4. Thus, the output here is false. Now let's examine another example. In the given grid, there is indeed a cycle. The path starts at cell 0, 0, then moves to 0, 1, proceeds to 1, 2, continues to 2, 1, then to 2, 0, and finally loops back to 0, 0. This path forms a closed loop, and its length is greater than or equal to 4, so the output for this grid is true. This demonstrates how the cycle detection works when paths traverse diagonally or take multiple turns, as long as they ultimately loop back to the starting point. When solving this problem, it's important to consider the given constraints. The grid dimensions m and n can go up to 500, so our solution needs to be efficient to handle larger inputs. Each grid cell contains a single lowercase English letter, so we only need to check character matches. Edge cases to keep in mind include grids with only one cell, where no cycle is possible, or grids where all cells contain distinct values, which also cannot form cycles. Additionally, paths that may look like cycles but have a length shorter than 4 should not qualify. These considerations will help ensure our approach is robust and accurate. To solve the problem of detecting cycles in a 2D grid, one straightforward approach we could consider is brute force. The intuition behind this method is to examine all possible paths within the grid. Starting from each cell, we perform a depth-first search to explore paths of length 4 or more. During this process, we keep track of visited nodes and check if we return to the starting cell. If the DFS traverses at least 4 nodes and revisits the starting point, we can confirm the presence of a cycle. However, there are important precautions to take, such as avoiding revisiting the immediately previous cell within the DFS, which could lead to false cycles. The major drawback of this approach is its computational expense. The DFS would need to exhaustively explore all potential paths, resulting in exponential time complexity. Specifically, in the worst case, the complexity is m*n*, asterisk 4 caret, m*n, where m and n represent the grid dimensions. This makes the brute force approach infeasible for large grids, especially as the search space grows exponentially. Additionally, it incurs m*n, space complexity for the recursion stack, further limiting its practicality. Instead of brute force, we can optimize the solution with a refined DFS designed specifically for efficient cycle detection. The key steps involve starting a DFS from every cell, while keeping track of the previous cell to avoid revisiting it immediately. This ensures that false cycles are eliminated. A visited matrix is used to mark cells during the current DFS path. If we encounter a cell that has already been visited and it is not the immediate parent, we can conclude that a cycle exists. Another important condition is that the path must have a length of at least 4 before we check for cycles. This approach also leverages the fact that the grid contains only lowercase letters. We can skip DFS from cells with characters that don't match the starting cell, further pruning unnecessary paths. By doing so, each cell is visited at most once per DFS, leading to a time complexity of O(m*(n). The space complexity remains O(m*(n) due to the visited matrix and recursion stack. This method is particularly effective because it takes advantage of the problem constraints, avoiding the exponential behavior of the brute force approach while maintaining simplicity and efficiency. An alternative strategy to detect cycles is to use the union-find data structure, also known as disjoint set union. Here, each cell in the grid is treated as a node, and edges are created between neighboring cells that share the same character. The idea is to union these neighboring nodes, and if two nodes that are already connected attempt to union again, it indicates the presence of a cycle. This method is highly efficient for detecting cycles in graphs, and the grid can be interpreted as an undirected graph where edges exist between adjacent cells with the same character. However, there are trade-offs to consider. Union find is generally more suited to static graphs, whereas in this problem, the traversal dynamically processes edges. Additionally, implementing union find for a 2D grid requires extra bookkeeping to map 2D indices to a 1D representation, adding complexity. The time complexity of this approach is O(m*(n)alpha, m*(n), where alpha is the inverse Ackermann function, and the space complexity is O(m*(n) for the parent and rank arrays. While union find is a viable alternative, it is less intuitive in this context compared to DFS. The need to transform the grid into a graph structure adds complexity, which makes it less appealing for this specific problem. After evaluating the potential approaches, the optimized DFS with cycle detection stands out as the most suitable strategy for this problem. This method directly leverages the grid structure without requiring additional transformations, making it both intuitive and efficient. By pruning unnecessary paths early using character matching and tracking visited nodes, it avoids the exponential complexity associated with brute force. The trade-offs between the approaches further emphasize the advantages of this method. While brute force is simple to conceptualize, its computational inefficiency makes it impractical. On the other hand, union find, though efficient for static graphs, introduces additional complexity when applied to dynamic grid traversal. The optimized DFS strikes the right balance, offering simplicity, efficiency, and alignment with the problem's constraints. This makes it the best choice overall for detecting cycles in a 2D grid. In this problem, we are given a 2D grid of characters and need to determine if there exists a cycle consisting of the same character. A cycle is defined as a path that starts and ends at the same cell, visits at least 4 cells, and moves only in the 4 cardinal directions: up, down, left, or right. To solve this, we use depth-first search, or DFS, combined with backtracking to explore all potential paths. The first step in the algorithm is to validate the input and initialize essential data structures. Specifically, we read the dimensions of the grid, N4 rows and M4 columns, and create a 2D Boolean array called visited. This array helps us track which cells have already been visited during the current DFS traversal. These initializations lay the foundation for the DFS process that will follow. Next, we define the DFS function, which is the core of the algorithm. This function takes several parameters: the current cell, x, y, the starting cell, start_x, start_y, and the depth representing how many cells have been visited on the path so far. For the base case, if the depth is at least 4 and we return to the starting cell, we have successfully detected a cycle. Each time we visit a cell, we mark it as visited. After marking the current cell, we proceed to explore its neighbors. Using the 4 cardinal directions, we calculate the new positions, new_x, new_y, and check if they are within the grid boundaries. If the character at the new position matches the starting cell's character and the cell hasn't been visited yet, we recursively call the DFS function to continue the exploration. Additionally, if a neighbor matches the starting cell and the depth is at least 4, this is another indication of a cycle. Once all valid neighbors are explored, we backtrack by unmarking the current cell, allowing it to be reused on other paths. Finally, we loop through each cell in the grid, starting a DFS traversal from any cell that has not already been visited. If a cycle is detected during any traversal, we can immediately terminate and return true. After processing all cells, if no cycle is detected, we return false. This brings us to some key insights about the algorithm. First, a cycle requires visiting at least 4 cells, so we only check for cycles when the depth reaches this threshold. Returning to the starting cell after meeting this requirement is what confirms a valid cycle. The efficiency of the DFS approach is enhanced by the visited array, which ensures we don't revisit cells unnecessarily within the same path. Backtracking further allows us to explore all possible paths without permanent markings. We also implement early termination, exiting the algorithm as soon as a cycle is found, saving computational resources. Finally, several edge cases must be considered, such as grids with only one cell, grids where all characters are the same but disconnected, and grids where the number of rows and columns differ. These scenarios highlight the robustness of the algorithm. To implement the algorithm effectively, we rely on 3 main data structures. The first is the visited array, a 2D Boolean array that tracks whether a cell has been visited during the current DFS traversal. This prevents revisiting cells in the same path and ensures correctness. The second is the grid itself, a 2D array storing the input characters, which we access in constant time. Finally, the recursion stack, which is inherent in the DFS process, facilitates backtracking as we explore different paths. Now, let's analyze the algorithm's complexity. The time complexity is determined by the grid size and the DFS exploration. In the worst case, we visit all cells, and each DFS call explores up to 4 neighbors. This gives us a time complexity of O, n*m, where n is the number of rows and m is the number of columns. The space complexity includes the visited array, which requires O, n*m, space, and the recursion stack, which can also reach a maximum depth of O, n*m in the worst case. Let's walk through an example to see the algorithm in action. Consider the input grid, B, We start the DFS from cell 0, 0, which contains the character A. From here, we explore its neighbors, such as 0, 1, and 1, 0, marking cells as visited as we go. The traversal continues, and we eventually return to the starting cell, 0, 0, after visiting at least 4 cells. This satisfies the conditions for a cycle, so the algorithm outputs true. This example illustrates how the algorithm efficiently detects cycles by leveraging DFS, backtracking, and the visited array to ensure accuracy and performance. Here, we begin by defining the class solution and the method contains cycle, which will determine whether there is a cycle in the given 2D grid. First, we calculate the dimensions of the grid using len, grid, for the number of rows and len, grid, 0, for the number of columns. These values will help us handle grid boundaries efficiently during traversal. Next, we initialize a visited matrix of the same dimensions as the grid, where each cell is initially set to false. This matrix will help us keep track of which cells have already been visited during our traversal. Now, we define a helper function DFS for depth first search. This function takes the current cell's coordinates, the coordinates of its parent cell, and the character we're currently exploring. Inside the function, we first mark the current cell as visited in the visited matrix. Then, we define the possible directions for movement, right, down, left, and up. Using a loop, we compute the new coordinates for each direction and check if they are within the grid's boundaries. If they are, we further verify if the character in the new cell matches the one we're exploring. If it does and the cell is already visited but not the parent cell, we've detected a cycle. In such a case, we return true to indicate a cycle exists. If the new cell hasn't been visited yet, we recursively call the DFS function for this new cell, passing its coordinates as the current cell and updating the parent's coordinates. If any of these recursive calls returns true, it means a cycle has been found, and we propagate this result back up the recursion stack. If no cycles are detected after exploring all directions, the function returns false. After defining the DFS function, we iterate over each cell of the grid using nested loops. For each unvisited cell, we initiate a DFS traversal by calling the DFS function with the current cell's coordinates, setting the parent's coordinates to -1 since it has no parent initially, and passing the character at the current cell. If any of these DFS calls returns true, it indicates the presence of a cycle, so we immediately return true from the contain cycle method. Finally, if we complete the entire grid without finding any cycles, we return false, as this means no cycles exist in the grid. Here, we begin the Java implementation of the solution to detect cycles in a 2D grid. First, we import the necessary utilities and define our class solution with the method containCycle. This method takes a 2D character array, grid, as input. We start by determining the dimensions of the grid, rows and calls, and initializing a visited array to keep track of the cells we've already explored. Next, we define a helper method, DFS, which will perform a depth-first search to detect cycles. The parameters for this method include the current cell's coordinates, x and y, the coordinates of its parent cell, parent x and parent y, and the target character, target char, which helps ensure we only explore cells with the same value. Inside the DFS method, we mark the current cell as visited and define the possible movement directions, right, down, left, and up. Using these directions, we iterate over the neighboring cells. If a neighboring cell shares the target character and is within bounds, we check if it has already been visited. If so, and the neighbor is not the parent cell, a cycle is detected, and we return true. Otherwise, we recursively call the DFS method on the neighbor. If any recursive call detects a cycle, we propagate that result back by returning true. If no cycle is detected during the DFS traversal of a neighbor, we continue checking other directions. Once all possible moves have been explored, the DFS method returns false, indicating no cycle was found starting from this cell. Back in the containCycle method, we iterate through every cell in the grid using nested loops. For each unvisited cell, we start a DFS traversal by calling the DFS method, passing the current cell's coordinates, -1 for the parent coordinates to signify no parent, and the value of the cell as the target character. If the DFS call detects a cycle, we immediately return true. If no cycle is found after examining all cells, the method ultimately returns false, indicating the grid does not contain any cycles. This approach ensures that we perform an efficient traversal of the grid while detecting cycles based on the connectivity of characters. To start solving this problem, let's examine a simple 2x2 grid with no cycle. The input grid consists of 2 rows and 2 columns, with characters A and B. We first initialize the dimensions of the grid as rows equals 2 and calls equals 2. Next, we create a visited matrix, which keeps track of whether a cell has been processed during our traversal. Initially, all cells are marked as false since we haven't visited any of them yet. We then begin iterating over all the cells in the grid, starting with cell 0, 0. At cell 0, 0, we observe that it hasn't been visited, so we start a depth-first search, DFS, from here. The character in this cell is A, so we mark it as visited in the visited matrix. Now, we proceed to explore its neighbors. Looking to the right, at cell 0, 1, we see that the character matches A, so we recurse into this cell to continue the DFS. At cell 0, 1, we mark it as visited as well. Checking its neighbors, we find that the left neighbor, cell 0, 0, has already been visited. However, since 0, 0 is the parent of the current cell, we confirm that this does not form a cycle. Next, we examine the downward neighbor of cell 0, 1, which is cell 1, 1. Since the character in this cell does not match A, we skip it and conclude the DFS for this path. At this point, no cycles have been detected, so the algorithm continues to check all other cells in the grid. After completing the traversal of the entire grid, we find that no cycles exist. Therefore, the result for this example is false. Now, consider a slightly larger 3x3 grid where a cycle is present. The grid contains a mix of characters, but most cells contain the character A. We initialize the grid dimensions as rows equals 3 and calls equals 3, and create a visited matrix where all cells are initially marked as false. Beginning at cell 0, 0, we start a DFS since this cell has not been visited. The character is A, so we mark it as visited. During the DFS, we explore its neighbors in a recursive manner. This traversal takes us through cells 0, 1, 0, 2, 1, 2, 2, 2, and 2, 1. At cell 1, 1, we revisit cell 0, 1, which has already been visited and is not the parent of the current cell. This indicates that a cycle has been detected. As soon as we detect the cycle, the algorithm terminates and returns true. Finally, let's look at another 3x3 grid, but this time without any cycles. The characters in this grid are all distinct, so there are no neighboring cells with the same character. As we traverse the grid, each cell is visited exactly once, but no cycles are formed because no set of connected cells with matching characters loop back to an already visited cell. After completing the traversal of the entire grid, we confirm that no cycles exist. The algorithm returns false for this example. In this solution, the time complexity is determined by the size of the grid, which consists of m rows and n columns. The outer loop ensures that we iterate through every cell in the grid, a total of m*n cells. For every unvisited cell, a depth-first search, or DFS, is initiated to explore connected components. During the DFS, each cell is visited at most once, thanks to the use of the visited matrix that prevents revisiting. This means the cumulative time spent across all DFS calls is proportional to the total number of cells in the grid. As a result, the overall time complexity is O(m*n), ensuring that the algorithm scales linearly with the grid size. To further elaborate, each cell in the grid is processed in constant time during the DFS traversal, as it involves checking up to 4 neighbors. This means the work done per cell is O(1). When multiplied by the total number of cells, m*n, the total time complexity becomes O(m*n). Whether the grid is entirely uniform or consists of completely isolated cells, the algorithm's efficiency remains consistent. In the best case, a single DFS call traverses all connected cells, while in the worst case, each cell forms its own component. Regardless of these scenarios, the time complexity remains O(m*n), demonstrating the robustness of the algorithm. Now let's discuss the space complexity. The solution relies on a visited matrix to track which cells have been processed. This matrix matches the dimensions of the grid, requiring O(m*n) space. Additionally, the DFS recursion stack contributes to the space usage. The depth of the recursion stack corresponds to the size of the largest connected component in the grid. In the worst case, this depth can be as large as all m*n cells, requiring another O(m*n) space. Therefore, when you combine the space needed for the visited matrix and the maximum recursion stack depth, the total space complexity in the worst case is O(m*n). When analyzing memory usage, the visited matrix is typically the most significant contributor to space complexity, as it must account for every cell in the grid. The recursion stack, while theoretically capable of reaching the grid size, is often much smaller in practical scenarios. Comparing this optimized DFS approach to a brute force method highlights the efficiency gains. A brute force solution might explore all possible paths from each cell, leading to exponential time complexity, specifically O for m*n, given the 4 possible directions. The DFS approach avoids this inefficiency by using the visited matrix, ensuring that each cell is processed only once, reducing the time complexity to O(m*n). The DFS algorithm is particularly well suited for detecting cycles in a grid due to its ability to efficiently traverse connected components without revisiting cells. The visited matrix ensures that no cell is processed more than once, and the recursion stack depth remains manageable in most practical cases. The space complexity of O(m*n) is optimal, as it's required to store the visited state of the grid. In summary, the DFS-based approach achieves a linear time complexity of O(m*n) for all cases and a space complexity of O(m*n), making it significantly more efficient than naive approaches while handling the problem's constraints effectively. One of the most common mistakes when solving this problem is ignoring edge cases. For example, you might overlook scenarios like empty grids, grids with only one cell, or grids where all cells have the same value. These special cases can easily cause your solution to fail, so it's critical to test for them explicitly. Another frequent issue is infinite loops in your depth-first search. This can happen if you forget to track visited cells or if you incorrectly manage the process of marking and unmarking cells during backtracking. It's also important to optimize for early exits. If you already know that a particular path cannot lead to a valid solution, continuing to explore it wastes valuable computation time. Pruning techniques can help you terminate these unnecessary recursions early. Additionally, it's easy to confuse paths of a certain length with actual cycles. Remember, a cycle must connect back to the starting point. Finally, hard-coding grid dimensions is a risky assumption. Grids can be non-square or vary in size, so you should always determine their dimensions dynamically using functions like len, grid, and len, grid, 0, to ensure your solution is robust for different inputs. When preparing for interviews, it's important to understand that grid-based problems frequently appear in various forms. These might involve depth-first search, breadth-first search, or even dynamic programming. Variations could ask you to find the largest connected component, discover the shortest path, or detect specific patterns in the grid. Beyond solving the problem, you should be ready to explain your approach clearly. For instance, when using DFS or BFS, you might note that the time complexity is O, and *m, for a grid with n rows and m columns. If the interviewer asks about further optimizations, discuss techniques like memoization or alternative data structures. Another key aspect is asking clarifying questions upfront. Confirm details such as whether diagonal movements are allowed or if cycles can overlap. Missing these constraints can lead you down an unproductive path. Finally, always try a practice run on a small example before diving into the code. This step can help you identify potential logical errors early in the process. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 200, number of islands, involves counting connected components in a grid, which is similar to detecting cycles. LeetCode 130, surrounded regions, challenges you to modify specific regions within a grid based on connectivity rules. Another great example is LeetCode 79, word search, which focuses on finding a specific sequence in a grid, and LeetCode 695, max area of island, which asks you to calculate the size of the largest connected region. In terms of alternative approaches, brute force with DFS is straightforward to implement and works well for small grids. However, it quickly becomes inefficient as grids grow larger due to the exponential number of paths it explores. The trade-off here is that while the implementation is simple, the space complexity can be high due to the recursion stack. Another method is using union find, or disjoint sets, which is excellent for cycle detection in undirected graphs. However, adapting it for directed graphs or problems with specific path constraints in grids can be quite challenging. While it's more efficient in some cases, it's less intuitive for handling path-based constraints. Dynamic programming is another powerful technique that can optimize repeated calculations, especially in grid problems that involve counting paths or maximizing values. The trade-off here is that designing the state representation can be tricky, and it may not always fit problems focused on cycle detection. Breadth-first search, on the other hand, is particularly useful for finding shortest paths or verifying specific constraints in a grid. However, it's less efficient when you need to explore all possible paths exhaustively. Additionally, BFS often requires supplementary data structures to track visited states and paths, which can add complexity to your implementation. Understanding these trade-offs is key to selecting the right strategy for a given problem, especially under time constraints in an interview setting. Great job! To summarize, we tackled the problem of detecting cycles in a 2D grid, explored different approaches, and highlighted key concepts like graph traversal and optimization. Remember, practicing these types of problems will sharpen your problem-solving skills. Thanks for joining, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!